in this session. The first one is Mr. Manna. Just a small request, a special request from this particular, and it is with the permission of the speaker that I'm sharing this. So the speaker has some issues. That is why if you asking a question, please raise your hand. Our volunteer will hit you with a mic. Please speak slowly and clearly into the mic. That is all. Okay. So first up, consistent subset trees and interval graphs. Thank you. Okay, please take it over.
Thank you. Am I audible to everyone? Thank you for giving the opportunity to present the paper in FST 2024. I am Bill from Agriculture. I will discuss the consistent subset in trees and interval graphs. Here is the list of joint methods given. I am here to present the paper on behalf of Bill. So before going to discuss the definition of the consistent subset, I am going to discuss the nearest neighbor and vertex in set. Let's give a graph. Any graph. This is any graph. More than the shortest distance. D7. This is the shortest one. This is the shortest one also, right? So now, set is on the vertex set, the nearest neighbors the vertex B in set is vertices where the closest to is. I mean, those vertices which are closest to is, these vertices are actually the nearest vertices. I mean, the nearest neighbors. Example for this figure. Suppose S is V5, V6, V7, V8. That means this four vertices, suppose. So, that's nearest neighbors are V1, actually V6 and V8, not the V5. Because if you see the V1, this is the nearest because the distances these distances also too. So V6 and V8 will the same distance. But V5 same distance, which is distance is 3 actually. So that means V6 and V8 are 7 nearest vertices, 7 nearest neighbor for the vertex V1 in the set is. Describe the consistent subset. Set of colors C and 1 to C. That means input. One is a graph and the second thing is that set the color. For the set of colors 1 to C. Which is given. And this is only given. Subset of the vertex set set to be a consistent subset in the vertex set at least one of the nearest neighbors B in S has the same color as B. We already discussed what is the nearest neighbor, the vertex in the set. So now as we increase the color, so at least one of the nearest neighbor must have the same color as their dot. In this case, then we can say this S is a consistent subset. The target is to find out minimum such consistent subset. This is called the minimum consistent subset, MCS. Example, suppose this is a graph. And graph. And analysis. And colors here. Then C will be a 3. And C. Blue and green. Which is given? Which are given? Set S, the subset of the vertex set S, between B and B is not a consistent subset. Because if you see B line, then the subset S is actually B3 and we are different color. So this should be the same color of B. So B is level B3 color. So this S is the consistent subset. But this is the consistent subset. B6. B6 is what is this? Set is inside B5 and B11. This is same color, which is B5. So this is not this is not B6. This is B1. This is set is inside B2, B1, because same distance. This is also 2, this is also 2. So this is right. Next, set is. And this is same color, which is 2. Same process. But this S is a consistent subset. But this is a minimum consistent subset. This is also a consistent subset. But set one subset. But this consistent subset, I mean, the minimum consistent subset is not input. Consistent subset, example. Right. Consistent subset must have which one is called its color.
Can we wait for one minute? But when you say nearest neighbors, you mean the closest under B. B is just an edge distance.
Yes, this is the edge distance. This is the edge distance. At same distance. Right? This consistent subset is that consistent subset column is polynomial consolvable. It's variable. But this is of the energy graph. Six. This see that just element sign of the minimum consistent subset, the number is 2. When it says algorithm, see vertices of the two and see the number of colors. Right? Others. This functions. The same number choose anything. See, I will tell you. C is the quantities. C six, which is significantly additional result. C C plus 3. Where C is the number of colors and A is the number of pieces. Exactly. I will going to discuss the empty complete quantities. What is the instead of the so instead of the yes. Satisfied. Suppose you have images. So there are some things like that. So what is this? The same color. This same color but different from the color like these lattices. So these are x1, x2, x1. Here are the m matrices and here are also m matrices. When S1 into S1 m, S1 to S1 m. So same as the color of S1 m bar. Same the color of S1 m is same as color of S1 m bar. Understand these vertices with x1 and these vertices with x1 bar, x1 1 bar. Vertices which are different from introduced. Understand x1 and x1 1 bar. Find out the consistent subset for this figure. We want to find out. Consistent subset must have which one corresponds to that. This is all in this figure. That's it. This is which one is in the solution. These vertices only have an additional in the solution. Similarly, all these two vertices. Suppose I identify this vertex and this vertex in the solution. Suppose. This is in the solution. These vertices would have only additional in the subset. That we are going to find this. Suppose S1. For S1, the nearest level is S1 1 bar. Different color. So it will be a consistent subset. That's also in the consistent subset. Right. Similarly, solution. This one of this and call this theorem is also at least one in the solution. How about we are going to put this one and this one in the solution? Suppose. This matrices and this matrices in the solution. I am going to put these matrices in the solution. Suppose. Then for these matrices, the nearest level 2, 3, this one, 1, 2, 3, this one. Because this one is distance 1, 2, 3, 4, 5 distance. This is also 4 distance. So that means for the S11, the set of nearest neighbors in the set are this one and this one. They are defined color. That means this one will be the consistent subset. That is, we have to this is the consistent subset. The solution. This is in the consistent subset. Suppose this one, suppose S11. For this one, we want to find out what this is in solution. Then 1, 2, 3, 4. So 1, 2, 3, 4. So 1, 2, 3, 4. That means this also 4. That means all the things are in the nearest neighbor. It's I am the square. All of these are the nearest neighbor. S11. S11. S1. I know. Nearest neighbor. This one, same so it is a consistent subset. Same but rules. I mean, these are the gadgets. These are three parts. The color of this one is same as x1. I mean, suppose this is x1 or x2. But this is coming from these vertices. Also, the color of this is coming from this vertex because this is so this is going to be x2. So for x1 it is coming from here. For x2 it is coming from here. Same thing we have did. But it's this. It's still up. It's still this can be right. Problem. But these are actually considered one positive integer and another negative integer. But it's this is squash. Does it? And we can go for it. This. Then the subset size at most this because these are very budget. This is n plus 2 variables. So sorry, n plus 2 vertices. N variables, n plus 2. Now, these are satisfied intervals. This is the solution. That is very good. What is this? That is very clean into minus k. And for this one is for this red color. So this one is NP complete our problem. But we shall discuss the activities. Suppose we this is of the t is n and every place of the t is covered by 1 to c is the parameter. So we have this. So now let's be in the vertex set. Suppose this is the subgroup set at P. This is a subgroup integral thing. Yes. So some children when you so children in general something these are the children. This These are the first. And each first, that's the this person is actually voted as I plus B. This person that is written in the B, this person voted I. This one. This one. You know that. Because so this one this is actually 12. So this person is 12. This is 12 plus 1B. So consistent subset of T with the right consistent subset T. So this consistent subset is master sentences is out version, is E version, and C version, and T version. This sentences is this is C for this and is out for this. That means C is C and is out is actually that's this is in this is it. So and sentences on the next level which is ceiling. Okay. So means C, S and S out of these two parts. That means we are going to consider 6 parameters here. Now each choice of the E, because for every choice of B, every one is D. Simplified. And it gives us the result of 50. Yes, then we set it on the and also the input content. So in the other graphs. Yes. The graph has degree exactly 3. So this is the graph. It's B1. This gadget. Happens B1 others. Now, this is a simple lecture, right? Anyway, the same. So this here. Okay. So when we get small intervals, this when we get small interval, which are not mutually intersecting, that means the small intervals are not intersect each other. But when small intervals, the same. Then adjacent to each other. How do you understand that? The all this length. Also, we can say large interval. The large interval. So this is this big small intervals. These are the small intervals. Small intervals accepting. Representing the last interval. That means the last interval just and all the small intervals, all medium intervals. Then the last interval should be different. We should have intervals adjacent. Okay. This is that the graph was a better score offset at the most, better score at the most, the consistent subset, then the consistent subset offset at the most, k into 3 plus n cube. This is our result. And the conclusion is that so is the algorithms, express algorithms, and 6 7 plus takes are cycle gaps. Is there any other algorithms? Thank you for your attention.
Questions? Tree graphs, have you considered that?
Yes, they are it's not only till now, but yes, this was a very good question that called the bandit tree graph. Yes, correct.
Any other question?
Worst case depends on how large S has to be for, for some class of graphs. Like I'm not looking for the exact S, but just worst case bounds on how large the S has to be.
I don't understand. Can you please repeat the question?
So it's when you look at some class of graphs, let's say two. Let's say yes. The S has to be.
Okay.
How such bounds? You see
Okay, how much the S can be? How S can be? What size S can be? That can be.
graph.
This can be. But this is this is another way. This is the same zero. This is a subset. But the minimum subset always exist. This also always exist because this is the state. This is also a consistent subset.
So you show harness on these easy so harness stuff. So what are the results if you have intervals or some constant number of intervals? Yes.
Okay, so we have a Daniel that I have to do the next algorithm. Which algorithm is to do 6C into the frequency plus 3. So if you when we do the 3,
ultrasound.
Questions? Next time, just speaking again.
Yeah, Vincent?
Question. I haven't asked for that. So, is the non-consistent subset unique? That's the question. Everybody is attentive. Okay. Cool. Speaker. Thank you. Not unmuted.
How to change this slide?
Okay. This is next, and this is previous.
I just want previous and next, that's all. This will work, right?
Yeah, that this one also actually.
Can you please tell me? This one is,
This is just a pointer actually. So you are
okay,
so
this will work.
can
Right?
do it with
And this is next, is it?
yes,
This is,
the bigger one. Yeah, that is next. This is next, and the lower one is previous.
this, I think this both to work.
Okay. That's also.
No,
This is
something,
next
something.
one.
Yes, sir.
Yeah, this is next only, and this is previous.
How to go to first? Okay, I'll mail it.
Okay. The next topic is parametric algorithms and hardness for the maximum HQ coloring problem that will be delivered by Shashikant.
Good morning, everyone. I think I'm audible, I think. I'm a PhD student working with Dr. Rose Matthew and Fahad Palal. Today, my talk is on graph coloring problem, maximum HQ coloring. Maximum HQ coloring problem. HQ coloring is a type of graph coloring which will satisfy three conditions. First thing is, it is a coloring on edges. Second thing is, it is a maximization problem. I need to give maximum number of colors to the edges in such a way that at every vertex, the incident edges can be colored only with at most Q colors. So consider the following examples. Take a path graph. The degree is at most to 2. So I'm considering a maximum H2 coloring of the graph. So at every vertex, I can give at most 2 colors incident edges. So it means like every edge is given one new color. So for a path graph, it would be -1. And this edge 2 coloring or HQ coloring will not necessarily be proper. So at every edge, I can color with, but I can color the incident edges with at most one color. So entire graph can be colored with one color. And this is a maximization problem. Otherwise, there is no challenge. If I valid HQ coloring, it means at every vertex I can give at most Q colors. So with one color, I can color the entire graph. So it will become a trivial thing. So the challenge is to come up with maximum number of colors that can be given to the edges, satisfying this one condition.
And consider the what I will do is at every vertex, unlike the root node, I will give one new color descendant edges. Whereas in the root node, I do colors. So here, the number of colors I need to maximize is 8. Consider K3, complete block on 3 vertices. For maximizing the number of colors for valid edge 2 coloring with K3, every edge is given one new color. Now, I put the 4th vertex in K4. So, the incident edges on vertex 4, consider this as vertex 4, would be forced to be given the colors shared by the other neighboring vertices, because already at any vertex in K3, we have the color 2 condition is satisfied. Like already at this vertex, red and then some blue. At this vertex, 2 new colors are there. At this vertex, there are 2 new colors. So this 4th vertex has to share neighboring colors. So for K4, the optimal number of colors would also be 3. One big thinking exercise would be what would be at least for an upper bound on Km. So the earlier work, the work is inspired from Goel, Kamat and Mishra. It's an MSCS 2013 paper. They discussed FTT algorithm based on 2 parameters for this coloring problem. One is standard parameter and other is dual parameter. The question is, given a graph G, can I the decision version? Given a graph G, can I color with 2 colors? Now, other version is, given a graph G, can I color with n-n colors? So, consider 2H coloring of graph. So, when there's a 2H coloring, at every vertex, I can be exposed to 2 colors. So, one you can infer is, so at every vertex, I can give 2 colors. So 2 into total number of vertices, because there is double counting, then the upper bound would become n. So how short from this upper bound is the optimal number of colors or the number of colors. So that is the dual parameter. So given a graph G, and the parameter is n minus L, other parameter is L. Now, consider the graph G. In this graph, the brown colored edges are the matched edges. And this constitute the maximum matching of the graph G. Now, for this coloring problem, if a valid G2 color, I want to find out the optimal number of colors. Now, it is easy to observe that this optimal number of colors would be at least maximum matching. Because consider maximum matching, distinct color for every independent maximum matching. And every other edge would be incident on the matched vertex. So you only color rest of edges. So here, let's say the matched edge is represented by brown color. So do one new color to all these matched edges, and then do another distinct color to the matched edges. So the upper bound for optimal number of colors in this coloring would be at least maximum matching. So we call this, so optimal number of colors is equal to maximum matching plus K. So we can again think of this coloring problem based on this parameter K, which we call as other guarantee parameter. It is like how number of colors I need this maximum matching. So that will also constitute one parameter. And in the same paper, Kamat, Mishra and MSCS 2013 had asked if there exists an FTT algorithm for the parameter K, that is the dimension, how many colors more than maximum matching would I need to color the graph G. So we show that this problem, parameter by K, parameter is the relevant part. Consider this scenario, like the same paper, we observed that this coloring can be expressed in one-order, second-order logic. So, it is easy to observe that the period of a graph G is upper bound with the number of colors. And it is a good thinking exercise by doing upper bounded by K, because the period is at most vertex color of the graph. where in every bag I keep vertex cover plus add one edge, one vertex of any graph. So any edge can be seen in that bag, and then vertex cover is upper bound with the maximum matching. And maximum matching, and the optimal number of colors is at least maximum matching, because like the other case should be trivial in this instance. So given this hypothesis, by causal theorem, we can say that there exists an FTT algorithm parameterized by truth as parameter and then optimal number of colors. Since we have observed that, actually the paper has observed that the truth is appearing by K, so the paper gives an FTT algorithm by K. But then for some graphs, this algorithm becomes exponential in L, because like for some graphs, consider a path graph, if you stream it very low, and this one, so K is one, so it becomes exponential in N. So we come up with, so basically, can we think of an FTP algorithm? Each parameter is FTP algorithm. This result, for this problem, we come up with an FTP algorithm based on the bottom of the program. Basically, behind this algorithm is as follows. Consider the notion of separation. Consider a given graph G. Separation A comma B with A, B, some subsets of vertex set of edges such that vertex set of G is A and B. Consider separator. It is just the normal notion of the separator. We will remove such subset of vertices whose will make graph disconnected. So, other way to think about this is consider the separation A comma B. Exists just like with one vertex incident in A set minus B and other vertex in B set minus A. This is a separator. If such exists, then why this is the separator? So it is by definition. Now consider tree decomposition. We know that for any given graph, we have a tree decomposition given by gamma equal to ordered pair of P comma set of all sets, which is a subset of vertex set of a given graph G, where each set xt I call as a bag at any node in the tree. I call vertex of as node for convenience sake, and vertex as vertex of graph G. So it is an added pair of P comma set of all xt for all t in V of t. So consider this is the tree in the tree decomposition tau, and the size where XR is some set of vertices, and consider this subtree T2, which is a dark-line part, T2, T2 by T, and this T is XT. Now, consider VT is set of all vertices in all the bags in T2, and V2 is the subclass of G into the vertex set VT. So these are all the basic notations which I am going to use in my further talk. Now, given the tree decomposition, the tree of the tree decomposition constitute the separator. And other way of saying this is, there cannot be any edge starting from this part to the rest of the graph. That is, from with one vertex in this V2 minus XT, rest of the graph, which is V minus VT. So basically, I'm just saying that there cannot exist like this. So this is the base, same thing I'm saying. Consider it as the vertex set of T2, rest of the graph. This way there cannot be edge like this. And then the basic idea of this bottom up T2 is as follows. I'm considering a case of valid QH coloring, and I want to find optimal number of colors. So one important observation is consider the red colored edge here, which appears in A minus xt. Note that given is this vertex set Vt of Pt, and then B is the rest of graph, and this bag xt at a particular node in the tree of composition constitute the separator, and consider some edge in A minus xt. Say that color is red, and that color, a particular color xt is not present on any incident edge or any vertex in xt, then my claim is that that color will appear in 60. The reason is very simple. I'm hypothesizing maximum HQ coloring. Here, maximum HQ coloring. So I started with maximum, given someone has given me a maximum Q8 coloring. So if there is some red color, why would I give a red color to some edge in B minus 60? Because it's a maximization problem, distinct color. So it means that any color given to any edge in A minus 60 can be easily forgotten. It won't, I want to say that these colors won't appear in the rest of the graph. So this is the basic intuition behind this bottom of BP. Now consider the green edge. So for this to appear in the rest of the graph, my claim is that this color should appear on any edge incident on any vertex in xt. If not, then it becomes this scenario. Suppose if it exists, then this through the separator, this color can appear in the rest of the graph. So this it means that in my algorithm, when I'm making recurrence solution for my dynamic programming, when I'm traversing from to bottom, from bottom to top, I don't need to remember the color of the edges, but only the color of edges incident on any vertex in the separator. So I just need to count with some terminative argument how many such coloring functions with some specific combination of colors incident on edges on any vertex in my tag at a particular level. So this can be easily counted. What I do is at any node when I want to make a calculation. So what I will do is I will use this set of colors, one for separator edges on any vertex in the separator, and other is the rest of the graph. Consider this scenario. So I can simply use two disjoint set of colors at least by recoloring them. So we can define a relation on set of all coloring functions. We consider coloring functions. Left side as f and right side coloring function as some g. Now observe that this gray part is my separator and the colors here is some red, green, and then violet, and then green. And here it is red, and then violet, yellow, violet, and then some gray color, I think. It's gray color. So these do not, they are not related to each other because they are different color combinations. And the incident edges on any vertex in xt. So it means that I can make a relation in such a way that class of f will have all coloring functions having the same color combination. So here f and g are not related. Here this and this are not related. And it is easy to observe that this relation constitute equivalence relation. And the number of equivalence class can be upper bounded by qk power qk into n power fn. Because like I told you, vertex in the x node, given that tag size is at most k, total available colors is qk. Because the upper bound is qk, but in vertex I can color with at most q colors. So QKCK at most whole power QK, and then polynomial. So we store basically one intermediate function for one equivalence class. Overall, we'll be storing O star of QK power QK, total number of coloring functions at any node. So finally, at the root node, we can output one Q coloring function optimum with optimal number of colors, because like we are considering all possible coloring functions for this coloring problem. So at the root node, I will get one particular coloring function for finding optimal number of colors. And since we are the number of coloring functions is up and down by this factor, the same would be the time and space complexity. And this is how the result, the idea behind our first result. And consider this follow-up and our second result is as follows. The follow-up question from the same paper, where the question asked is, if there exists an FTD algorithm for this coloring problem, then parameter is by K is our guaranteed parameter, K is how many more number of colors I need beyond this minimum maximum matching, and we show that the result is for Q equal to 2, whereas for general case it is still open, and we show that the problem is WM hard, and we do the reduction from independent set to other guarantee H2 coloring in poly time using this gadget. The question is like, I think everyone must be knowing that independent set problem given V does there exist an independent set of size L. So basically we reduce from independent set, which is WM hard, using a polynomial gadget to our problem and show that it is WM hard. And if we want reduction details, you feel free to discuss with me offline. Thank you for listening. Any questions, please ask.
Time for a couple of questions.
Approximation algorithms for this?
We did not think on in that direction, but I still have some open questions. I did not think on that.
But for example, like if you take the like some variation of a greedy algorithm, do you know how poorly it might perform? Could it be very bad or
Greedy mostly fails, as everyone knows. Maybe the counter case can be easily cooked up.
okay?
Some open questions would be for Q, for general Q, what is the W1 hardness? And then what is the efficient, is that, some problems with itself has the best time complexity. So this also has that form. Okay. So something which proves that this is the best time complexity.
So the algorithm with respect to the maximum matching, the graphs.
So in this case, I'm considering only the bounded tree root graphs.
Yes, so my question makes more sense because, for example, how do you with graphs? Suppose it's always one of
We have showed that
approximation sense, right? So if you have a lot of matching, then you have a good approximation.
yes.
How do you with graphs where we have larger matchings in it? So decent approximation, say.
A couple of reasons by Alexander and Poka and Dvorak. I want to, but I don't remember. Like if we see this, sorry, sir, if you have this greedy approach for this, right? If you take this example for any tool, greedy approach would be the same line like this and two new to the root of this. Greedy approach. But fortunately, in Alexander which he showed that this greedy approach is optimum approach. The same question which you have asked. And so I think that if you go to the relevant papers, you can get a lot of information.
Thanks.
Thank you. Any other questions, please feel free to ask. Thank you.
Start to extend the speaker. Thank you. That's the end of this session.
Square graph and